is not applicable anymore. Okay, and the short column will behave differently because short column, when we apply the load, okay, and the stresses that happen will exceed the yield stress. So the column behavior becomes inelastic. Okay. So what we discussed until now, and what we discussed until now, the phenomena is on elastic buckling. Okay. Meaning that when we apply the column, if the column buckle, if you release the load, the column goes back to the original shape. Okay. That is elastic buckling. But in actual column, if it is short, okay, if it is short, then the load that we apply will cause us stress more than the yield stress before it buckles. So the column will behave inelastically. And to understand those columns, we need inelastic theory. Okay? We will not have time to cover that in elastic theory, but in the material that I share with you, they talk about how to consider inelastic behavior in the column. Okay. So remember that. So for slender column, the applied load reaches the Euler load before the axial stress exceeds the proportional limit. So the linear elastic analysis is therefore valid for slender column. So what we have discussed is valid only for slender column. The axial stress in the short column will exceed the proportional limit of the material before the applied load reaches Euler load. Okay. When it becomes short, if you use Euler load, the load will be very high. So it cannot reach this high load. Before that, the stress already more than the proportional limit and exceed the yield stress also. Therefore, the result of elastic analysis, what we have done here, consider elastic behavior, are not valid for short columns. Not valid for short columns. The buckling load of short columns must be determined by taking inelastic behavior into account. Okay. Okay. So take note of these limitations of all the discussion that we have. Okay, but elastic analysis will give you some estimation, approximations of what is the load that you allow the load to carry. Okay, but we do not allow the column to become inelastic. Now, before I end the first part here, I think I want to talk about this one method which can be used experimentally together with experiment to estimate buckling load. Okay, and this is called the Southwell plot method. Okay, it is a convenient, non-destructive method, so you don't have to fail the column to determine the buckling load. Okay. So what we do is we plot graph. We subject the column to axial loads. Then we measure, we assume the column already initially bent. Then we measure at the mid height here, what is the deflections, which is given by VC there. Then we also measure the load causing that VC. Then we divide VC divided by P. Then against VC divided by P. So we increase the load, we measure the VC, we increase the load again, we measure the VC, then we plot this graph here. So we have many, many points experimentally, then we try to fit a straight line through the point. And from the slope of this graph, we get approximation of buckling load. So this is called the Southwell plot method. Okay. So how come we can plot like this? There is a reason for that. Why we can plot a straight line to get to and the slope give us the critical load. It comes from these equations here. So it comes from this equation VC, which is the additional deflection at the mid height of the column. At the mid height of the column for an imperfect column under the action of P is given by this formula, where this is imperfection. This one we don't know. Okay. then we can rewrite these equations into a straight line equation form, which is y is equal to mx plus c. We can rewrite these equations into this form. Then, if you compare with the straight line equations, this is y, this is negative a is c, so x is this, okay? X is this, y is this. Then m will be the P critical. So that's why we can draw this straight line for many points of VC and VC over P. Let's say we take 10 points experimentally, then we draw the graph. Okay. So what I'm trying to ask you to do in the lab will be try to use this Southwell plot, try to determine the P critical. So I'm going to give you a sample. Let's say make of aluminium, different height, different length, okay? And then you try to press it, measure the deflections, press it again, measure deflection, press it again, measure deflections, and try to plot one graph and see the slope. From the slope, what is the P critical that we can get? And we try to compare with theoretical predictions. Okay? So this is a very convenient method. Okay? The method of Southwell plot. Okay? The basis is from these equations. The deflections at the mid-height of an imperfect column. So we can, in the lab, when you go to the lab, I think then we can try to see how good this will give us the predictions of the P critical. Okay? So that is the end of chapter 1. Okay? We have another. At least we have 2 chapters. Right? That is the end of chapter 1. Okay. Now, with the remaining time, what I want to go through with you is, we have not much time left, is introductions to a bit on behavior of what we call beam columns. Beam columns. So this is the second a bit introduction. First, this is the next topic that you need to know. Now, in so far, what we have discussed so far is a member, which is a column subjected to axial load. And our main purpose is to determine the P critical. We subject the column to axial load. Okay? Now, here the next topic that I want to cover is a member which is subjected to lateral load or end moment, which is causing the moment to bend, like in the beam, at the same time subjected to axial force. So this is beam column. Yeah, it combines 2 characteristics of actions due to the loading which is acting on the member. So this loading, which is lateral load, or this end moment here, will cause the member to bend. Okay? And this one will cause the member to compress. So they are together. So this member under these actions, without this, is like a beam. This member under these actions, without this, is a column. But if you combine them, we call them beam column. So beam columns are members that are subjected to both bending and axial compressions. So the bending can be caused by end moment. This end moment can come from the moment next to this, the member next to this, because this member might be connected to other member, and this end moment can come from the member next to this member, or the bending can be due to loading, distributed load, point load, or triangular load. Okay. And where can we see these kind of members is in frames. when you look at the frame structure, you have vertical member, horizontal member, inclined member subjected to vertical loads and lateral loads. So those members in the frame are example of beam column member, okay? Because they were subjected to both bending and compression. Now, there are two actions here. Yeah? There are two actions here. One is the bending, the other one is compression. But the primary actions is the bending. Okay, the primary action is the bending, which means this is the primary, this loading causing the beam to bend is considered the primary load. And the primary actions, the primary effect in the beam column is bending. Then on top of that, if you have this axial load, then you have an additional bending. Additional bending that we call the secondary effect. And we call that the secondary effect. Okay. So the primary is a bending. When you have bending, then it has additional. When you have bending, so this one will bend. Plus, if you have this, and then this multiply whatever bending deflection that we have, it causes additional moment. So that additional moment caused by this axial load when the beam bends is called the secondary moment, secondary effect. Okay. Now, what is the effect of P on deflections and internal force in beam column compared to if you don't have P, if you have a beam like this without P, if you have a beam like this without P, and with P acting at the same time you have this primary effect, what is the consequence? Okay? So that is shown by these two equations here. These two equations gives you the deflections and also maximum bending moment. So maximum bending moment for this case happened here at the midspan. This also happened at the midspan. And here delta O is the deflections without, in the case where there is no axial force. This M subscript 0 is the bending moment maximum at the midspan when there is no axial force. Then when there is axial force, you have this alpha here. For the deflection, I call it alpha subscript delta. For moment, I call it alpha subscript M. So this alpha here is what we call amplification factor. And because it is called amplification factor means when you have axial load acting on the beam, which is subjected to lateral load, the deflection will be increased, will be amplified. The same thing, the deflection amplified, the bending moment will also be amplified. It will amplify through this factor here. So what is a factor? We will look at when I meet you again next week. How does the factor looks like? Okay, what will affect the factor? This is the thing that we are going to look at when I meet you again next week. So the effect of having axial load on the beam column is the deflections and the bending moment will be amplified. Okay. So when we design for a member in the frame, we need to take note of this effect. Okay. So when we need to take note of this effect, we need to see how much is this being applied relative to P critical. If this is small, then the amplification factor might be small. If this is getting larger compared to critical load of this column, then the amplification factor might become larger. Okay. So, but how does the amplification factor look like? That's the next thing that we are going to look at when I meet you again next week. Okay. So this is the next topic that I'm going to look at, and this one is covered in here. In these notes, stability of beams under transverse and axial load. Okay. And also it is covered in chapter 3 of these notes here. Of this set of notes is covered in chapter 3. Okay. We finished chapter 1, not all. I think and then we skip chapter 2 first, we go to chapter 3. So this is 2, we will come back to 2 later. Chapter 3 is about beam column. Let's see. So if you want to read more here on this introduction part, where can you find beam column? You can find it here in under chapter 3 of this notes, and also under section 18.5 of this note. Stability of beams, they call it beams under transverse, forcing bending, and axial loads. Okay? So that will be the next thing that I will cover with you, and then we will see the amplification factor. How does it, what is the expression for the amplification factor? Okay. So with that, I think I will end the class today. Now, starting next week, our class on Thursday will start at 11, because my class with undergraduate students, the design class, is already finished this week. So we will go back to starting at 11. Okay. So that's all for today, class. I will end here. Okay.